this solid angle, remember that? Well, by using this and how to do that, solving it in, so it'll be the first question that we will do. So we're going to have to come back to this, right? So in the problem solving session of this lecture, we will solve question 5.1 using this probability current density, and we will get that the differential, the fraction of the incoming particles that get scattered through this solid angle. So d sigma d omega would be f naught squared. That's the same f as this f, as here, right? The scattering amplitude. So you just square it. So you get this expression. Alright, so we need to come back to that in the problem solving session. Okay, now, why talk about this? What's the point of talking about this? Well, this f here, f is, see, if we know what f is, I mean, have a look at this. This, that's essentially known, right? Well, that is. We know if we know k, r is pretty obvious. What's not known is the f. Right? What is this scattering amplitude? So you can use Schrodinger's equation, solve Schrodinger's equation, to find what this f actually is. Right? Now, I'll put that's a separate idea. Okay. Right? So essential idea is that you use Schrodinger's equation to solve for what f is. Okay, now in chapter 7, that's the angular momentum chapter, which is what, 2 chapters away from this one. We can solve not just for r and theta, but we'll do all 3 polar coordinates, r, theta and phi, and so that the wave function, it depends then on phi as well. And that means, like, if here's your atom, and you can, like, outer layers of the electron, they can have probability densities that have kind of loops, that depend on phi. And it's those loops that get used often in chemical bonding. They help the bonding. Which makes you wonder whether the whole thing's been designed. Okay. Alright. So now let's get down to the nitty-gritty of actually trying to start solving the Schrodinger equation. Now, so you take your wave function u. This will be a solution to your Schrodinger equation. We've done this sort of thing before, where we split up the wave function in terms of a spatial part and a time part. But for the last 4 chapters, we've been using only the spatially dependent, the time independent wave function. But here we're going to split it up, not in terms of spatial coordinates and time. We're going to split up the spatial coordinates into 2. One involving just r. R, remember, is the distance between the target and the scattering particle. And theta is the scattering angle. You may ask, why on earth is it put in this form in terms of cos theta, and what's this L? Where did that come from? Well, here's another example of stuff getting thrown at you. This L, in chapter 7, when we start doing, having a discussion on the quantum mechanics of angular momentum, you'll learn that angular momentum too is quantized, not just energy quantized. The angular momentum takes certain values, and a certain kind of angular momentum is spin, sort of like particles spinning on their own axis, kind of thing. They too have quantized values of their allowed spin. Now this L here that comes from one of the eigenvalues of angular momentum. So don't worry about it too much for the moment. Just remember these L's here, particular angular momentum quantum number, it's a value that tells you, gives you the value of the angular momentum eigenvalue value. In a similar way, like E1 or E2 or E3, those numbers 1, 2, 3, they are quantum numbers for the quantized energy. All right. Anyway, so these, once we've done chapter 7, the meaning of this L will become clearer. So this is a kind of foretaste, and throwing it at you, because we need to get into something about scattering theory. So it's a bit of the chicken and the egg. Which do you start first? All right. And these P's. What are the P's? Well, they are Legendre, a French mathematician. I guess quite a few French mathematicians were interested in polynomials as solutions to differential equations at the time, because there's a second polynomial type we've come across. These Legendre polynomials, they, again, have a look in chapter 7 on angular momentum and in Appendix B. So I guess when we come to do chapter 7, at the end of it, I'll probably have to do Appendix B as well, which talks about some of the math of the Legendre polynomials. But so you can, your wave function u, which you'll solve to find f of naught. And you need that f of naught to know what the wave function is for the scattering. Okay, so multi-step. All right. So that u you assume can be split in this way. So a position, an r part, an r-dependent part, and the theta, the angle part, but written in the form of Legendre polynomials. Now that's similar in nature to what we did with the simple harmonic oscillator in the previous chapter. Okay, well, we substitute this into u in the STI, the Schrödinger time independent equation. And we divide both sides, by this, and the r terms will cancel out, and the theta terms will cancel out in certain ways, and you're left with two equations, one involving the angle and the other one involving the r. Just similar to what we did before with the analysis on the simple harmonic oscillator. Now the r part, the equation that involves the r, looks like this. Now here, you've seen this sort of thing before. That's just del squared r. Now this is new. You may wonder what the hell's that? I'll explain it in a minute. This is familiar. Now remember, potential we're assuming is only a function of r. That's how we got this. The symmetry, so that the scattering depends only on the angle theta. It does not depend on the angle phi. Okay, so v is a function of r. This big R here is just here, right? And there's your eigenvalue. So eigenfunction, eigenvalue. Now we can simplify this down a bit by substituting variables. So let's define. Is that this? Yeah. So this k and this k I assume are the same. Right. So define k and I still need to memorize my Greek letters. This is chi, isn't it? I think that's the Greek letter chi. Isn't chi squared? That's in statistics. I've seen that in chi squared. Yeah. Okay. So that's chi. So you define chi, so the big R here is just chi over little r. Right? Just define that. It makes things easier. And your E, you define your k such that E equals h bar squared k squared over 2, and that's the mass Not quite sure why I didn't just put little m. That might be the centre of mass. It's a possibility. I mean, well, at the moment it's a detail. I'm not sure. I'll just gloss over that for the moment. Right. Okay. So choose your case. So this is true. Yeah, this is just the momentum, effectively, the de Broglie momentum. So momentum squared over 2 times. This must be some sort of mass, and that's the kinetic energy. That's the kinetic energy formula, momentum squared, z. And this equation then, you can rewrite, and that'll have to be for the next session, so we can rewrite this in a form that's more readily solvable, and that will be the next step, but that's the next session.